We're obsessed with sending humans to Mars, but there's a silent, deadly enemy nobody is talking about enough: solar radiation storms. These cosmic tsunamis could fry astronauts and equipment in an instant. The biggest challenge isn't getting there, it's surviving what's already there. And the solutions might surprise you. Mars's surface looks quiet: a red desert, a thin sky, dust on the horizon, and an entire planet that seems frozen in time. But behind that calm lies a danger that makes no sound, doesn't glow, doesn't appear on radar like a normal storm, and can still destroy a human mission in minutes. Mars's most efficient enemy is invisible. When we think of a solar storm, many people remember auroras on Earth, green and purple curtains dancing near the poles, something beautiful, almost romantic. But that's the domesticated version of the phenomenon. On Earth, most of the sun's violence is filtered by two massive defenses: a strong global magnetic field and a dense atmosphere. On Mars, these barriers do not exist in the same way. The planet has no global magnetic shield comparable to ours, and its atmosphere is so rarefied that it works more like a veil than armor. The result: radiation that becomes a spectacle on Earth becomes a sentence on Mars. The sun is not a light bulb. It's an energy machine working under constant tension. Sometimes that tension abruptly reorganizes and explodes. There are two main types of events that worry any mission on Mars: solar eruptions, called flares, and coronal mass ejections, known as CMEs. A flare is a burst of electromagnetic energy, a discharge that crosses space at practically the speed of light. A CME, on the other hand, is a punch of matter and magnetic fields, a colossal cloud of plasma carrying charged particles. When these particles pick up speed and arrive like an avalanche, the name shifts to something more direct: solar energetic particle storms. And here's a detail that changes everything. The radiation that scares you isn't the kind you can see. What truly threatens the crew is the flow of protons, electrons, and heavy ions that pass through structures, penetrate materials, and cause damage on a microscopic scale. It's as if the planet were being hit by a rain of projectiles so small you can't see them, but so energetic they can alter the function of a chip, cut a DNA strand, or turn a sensor into a noise generator. For a crewed mission, this is not theory. It's a countdown. Life on Mars starts with an equation that never balances perfectly: mass. Everything has to be light enough to leave Earth, but robust enough to survive in a hostile world. And radiation is the kind of threat that demands exactly what rockets hate: material, density, and thickness. Radiation shielding is not like sealing against dust. You don't solve it by tightening the joints. Energetic particles pass through structures, and the higher the energy, the harder they are to stop. To truly block them, you need to put stuff in their path. And putting stuff in the path means weight. That's why spacecraft and habitats tend to use compromise solutions. Water, food, and supply compartments are positioned strategically because these materials serve as extra protection. The goal is not to make everything invulnerable. It's to create a core, a storm shelter, a small space surrounded by as much mass as possible, where the crew can compress themselves during the worst particle peak. It's a simple idea, almost claustrophobic, but extremely rational. When the storm arrives, you don't fight it, you wait. Except waiting isn't so easy when the planet demands work outside. The classic vision of Martian colonization usually shows glowing domes, rovers coming and going, astronauts walking as if the outdoors were just a giant laboratory. In practice, every excursion is an exposure. Every activity on the surface is a calculated risk, because even if you build the habitat buried, protected by regolith, or use natural structures like lava tubes, there is a problem that doesn't go away: entry and exit. Human missions need external operations: repairs, assembly, collection, exploration, maintenance of antennas, panels, power systems, eventually construction. And it's precisely in those moments that an unexpected storm can turn routine work into a medical emergency. Now zoom in to the scale of the human body, where the threat gets even more serious. Ionizing radiation is not feeling unwell. At high concentrated doses, it can cause acute radiation syndrome, with effects that begin as weakness, nausea, immune suppression, and can escalate depending on dose and exposure time. At lower doses, but repeated over months, it increases the risk of cancer, cardiovascular problems, neurological damage, and changes that medicine is still trying to fully map in environments of microgravity and extreme stress. On Mars, exposure isn't a one-off event. It's a constant background, an invisible tide that never fully recedes. The storms are the giant waves on top of that tide. And even when the dose isn't immediately fatal, it can be operationally devastating. A debilitated crew on Mars doesn't have a hospital next door. There's no simple evacuation. There's no ambulance. Any reduction in performance becomes a risk multiplier. More errors, more fatigue, more time for tasks, more exposure, more consumption of resources. Now take that same event and put it inside the machines. Modern electronics are fast, compact, efficient, and also vulnerable. Energetic particles can cause what engineers call single-event effects. A bit that flips, a circuit that momentarily shorts, a memory that corrupts data, a sensor that starts seeing ghosts. Sometimes the system restarts and comes back. Sometimes it drops into safe mode, and sometimes the failure happens in the wrong chain. The wrong reading goes to the right controller, which triggers the wrong valve, which changes pressure in the wrong place, which forces a shutdown, which knocks out redundancy. In complex missions, disaster is rarely a cinematic explosion. It's usually a sequence of small failures that, combined, leave you with no margin. And here comes the most dangerous scenario: cascading collapse. A mission on Mars is not a single system. It's an artificial ecosystem. Power feeds heating. Heating keeps water and batteries within an operational range. Communications connect the crew to forecasting, guidance, and support. Navigation and control ensure that rovers and autonomous systems handle tasks without wasting resources. Air and water recycling sustain the duration of the stay. If a radiation storm hits the power system or causes failures in critical electronics, the mission doesn't just get harder, it can become impossible. And all of this is made worse by a factor no one controls: time. The longer the mission, the greater the accumulated exposure. The longer the stay, the higher the statistical chance of facing an extreme event. And here the sun's own context comes in. Solar activity grows and decreases in cycles of roughly 11 years. Near solar maximum, strong events tend to be more frequent. This doesn't mean every day will be a catastrophe, but it does mean the risk distribution changes. It's like crossing an ocean during a stormier season. You may have quiet weeks, and then a single day exacts the price for the entire choice. So how do we turn Mars from a fragile adventure into a truly habitable destination? The answer isn't in a single super material or a miracle technology. It lies in layers, redundancy, and forecasting. First, real-time space weather with better models and faster alerts. For a crew, minutes matter. An early warning can be the difference between being on the surface or already inside the shelter. Second, habitats designed to take the hit, with an armored core capable of sustaining the crew for hours or days without vital systems collapsing. Third, hardened electronics, resilient architecture, real redundancy, and procedures that assume failures as part of the scenario, not as exceptions. And there's a fourth element, perhaps the most underestimated: operational discipline. On Mars, the schedule has to obey the sun, not Earth's clock. External work needs to be planned with windows, rapid aborts, short return routes, and protocols that don't rely on heroism. Because heroism is far too costly when the enemy is invisible. Mars is a planet that tries to fool you with silence. It looks still, but it's exposed to space. And space is active, dynamic, and sometimes violent. The good news is that this violence is not a mystery. It can be measured, modeled, and to some extent, predicted. The real frontier isn't just the distance between Earth and Mars. It's our ability to build a human system that survives the environment exactly as it is, not as fiction has trained us to imagine. If you want more videos like this, going straight to the real risks and the solutions that can turn Mars into a possible next step, subscribe to the channel and turn on notifications. Because exploring other worlds isn't just getting there, it's staying. And on Mars, staying means learning to live with the danger you can't see. Don't forget to like and share. Thank you, and see you in the next video.